Take a look at this graph. If you had to describe what's happening to a car here, you might imagine it driving along a flat road, struggling up a steep hill, and finally parking at the top. In reality, that car could be driving on a road as flat as a pancake. The hill you see on the paper has nothing to do with the shape of the ground. We often struggle with these graphs because our brains want to treat them like a photograph of a landscape. Physics asks us to see them differently, as a record of a journey where the vertical height tracks a specific measurement, not a physical incline. To get the right story, try the hide the line technique. Use your hand to cover the actual drawing and look only at the label on the far left. That label tells you exactly which part of the car's motion you are tracking, turning a confusing squiggle into a clear set of instructions. Let's look at a distance time graph first. On the left, we have our road, and on the right, our graph. This setup tracks exactly where the car is at any given moment. When the car moves at a steady, unchanging speed, it covers the same amount of ground every second. This creates a perfectly straight diagonal line moving upward. If the car stops at a red light, time keeps moving forward, but the distance from the start stays the same. The line on our graph goes flat because the car is at rest. When the light turns green and the driver steps on the gas, the car starts covering more ground with every passing second. The line begins to bend upward, forming a curve. That curve represents acceleration. It's the mathematical version of that physical sensation where you feel yourself being pressed back into your seat. On this specific graph, the steepness of the line, the slope, is telling you how fast the car is moving. Now, everything changes if we swap that label to velocity. This tracks the car's speed, and it's the most common place to get confused. If you see a flat, horizontal line here, you might assume the car has stopped again, but the label says velocity, and that measurement isn't changing. The car is actually cruising down the highway at a perfectly constant speed. If the line starts angling upward in a straight diagonal, the speed itself is increasing. The driver is steadily pushing down on the pedal. You would see the needle on the speedometer climbing steadily. This is what uniform acceleration looks like on a graph. On a velocity graph, a flat line means steady speed, and the slope now tells us exactly how fast the car is accelerating. Velocity graphs also tell us the total displacement, or how much ground the car covered. The total distance is found in the physical space trapped between the plotted line and the bottom of the graph. We can calculate this easily by slicing that space into simple shapes, like a rectangle and a triangle. The rectangle represents the distance covered while the car was cruising at a steady pace. The triangle represents the extra ground covered while the car was actively speeding up. This geometric approach is a standard strategy in physics guides because it avoids the need for complex formulas. It's just simple math applied to a picture. Kinematic graphs aren't just abstract drawings. If you remember to check the label first and look for the shapes underneath the line, you'll see the real story of the motion every time.